Cool. Does it work? Okay, test. Let's see. Trackers incoming. Cool. Hello. Today we'll talk about conditional generative modeling, which is very exciting. But first, I want to say a few more words about the project proposal and about the assignment that is going to be posted today. I have very good news, which is that the assignment is going to be very little overhead for you. It's going to look as follows. So just for the record, on Thursday, the project proposals are due. I've posted some more guidelines again on Piazza, but basically what I said before, don't go overboard. The key point of the project is that you experiment, you engage with something we discussed in class. It's very broad. Anything that has to do with 3D. As I mentioned, I think my very straightforward projects are you can take any of the papers we discussed in class and do a tiny proof of concept implementation of it in a Google Colab. For instance, if you take the self-supervised monocular depth estimation in EvoMotion, that's a good candidate. Or FlowCam is maybe a little harder. Or anything that you think, even like the Gaussian spatting. Although someone asked me about the Gaussian spatting, that would be a very hard candidate to build a tiny version of. But that would all be good. I thought we had uploaded the CVPR template, but apparently we hadn't, so we are uploading it now. Is there, someone posted on Piazza that it wasn't uploaded. Is the CVPR 2022 project template uploaded? Has someone looked into that yet? Okay, good. So we'll post it today, and then you'll write a 1 to 2 page proposal using that template. The second part is the homework assignment number 4. So good news, it's going to be very little overhead. Homework assignment number 4 is basically going to be the following. In your project proposal, I have asked you to propose a first experiment. I said, please tell me what the first experiment is going to be that shows you that there are signs of life. Your assignment number 4 will be to write basically the forward pass of that first experiment plus the data loader, put it into a Google Colab, and that's going to be your submission. And we're just going to look at it, and we're going to run it. And it doesn't have to train or anything. I just want to see the forward pass and the data loader for your data set. That's basically going to be assignment number 4. So no extra overhead on top of your project proposal. But it does tell you that I do want the first experiment that you present in the project proposal will be somewhat reasonable. So in fact, maybe assignment number 4 is going to be write the project, write the first experiment, conceive the first experiment, and then, implement it in a Google Colab. It's going to be very, very easy. It's going to be mostly up to you, right, to do an interesting job with it. Does that sound good? Good. And we'll post the proper assignment with the proper instructions today. Great. Any questions on project proposal or assignment number 4? Because otherwise we're jumping straight in. Great. So this is, today we're talking about conditional generative modeling. Very exciting. What does that mean? Let's review our little framework for reconstructing 3D representations, right? We have said so far, we have a set of 2D observations, we do some kind of inference, we get a 3D reconstruction out, then we can differentially render it, and then we can supervise it in image space, right? The same framework that we've discussed 100 times by now in this course. Now let me ask you a question. Maybe Ayush has already talked a little bit about this paper, but today we're going to go in painful detail. If I show you the front of this fire hydrant, what does the back of the fire hydrant look like? It could look like this, or it could look like that, or it could look like that. And all of them are pretty similar, right? But if you look at them, they all have slight differences. The texture is different every time. If you would look very carefully, you could see that the geometry is a little bit different every time. The background, of course, is a little bit different every time. But if I showed you any of those and I asked you, is this a plausible reconstruction of the background of the fire hydrant, you'd probably say yes. All of these look plausible. But they're all different. So that's a problem. Because what that means is that inherently, this problem that we're tackling has uncertainty in it, right? And just to be clear, each of these has a corresponding 3D reconstruction attached to it. So not only could any of these be the back of this fire hydrant, but also for each of them, there's a corresponding 3D reconstruction that would generate that image, right? So the problem with the whole thing that we've been discussing so far is that the problem of 3D reconstruction from incomplete observations fundamentally is a problem that is uncertain. In other words, conditioned on the observation, there's not just one plausible reconstruction, there's an infinite number of plausible reconstructions. In other words, it's a probability distribution of plausible reconstructions. What that means is if you try to train any of the deterministic models, which we have discussed so far, PixelNerf, for instance, this is actually, in fact, PixelNerf. If you train a model like PixelNerf on scenes, on real-world scenes, like these fire hydrants, and then you ask it to reconstruct, for instance, this fire hydrant from a single image, then this is what you would expect to see. What you would expect to see is that for the input camera view, like for this camera perspective, from that camera perspective, you expect your reconstruction to be basically perfect. Because conditioned on the input image, there's no uncertainty in that view. You have seen every pixel. Of course, you can generate every pixel. But the moment you start moving the camera to positions that you haven't observed, for instance, you are disoccluding parts of the background. Suddenly, you're seeing a piece of the background that you haven't seen in the input image. Or maybe you're seeing the background of the fire hydrant, like here. And the moment that happens, suddenly, there is an infinite number of possible reconstructions of that part of the fire hydrant or of that part of the scene. And what deterministic models have to do, because they're trained with L2, they will usually give you the mean estimate under the loss that you have trained it with. So for instance, if you train it with an L2 loss, what will end up happening is that the model, and like what exactly you're collapsing the distribution over is a little bit tricky, but fundamentally you can imagine that this model basically takes the mean of all possible 3D reconstructions, and then that's the reconstruction it gives you. And that's why this reconstruction looks garbage, because it has to be blurry. It has to blur over all, that's what the mean means in this case. It has to blur over all possible 3D reconstructions. Does that make sense? Great. How do we fix it? Let's first review. So like this is a problem that has only been fixed very recently. And when I say very recently, I mean in the past half year. Reminds me actually, like, could have, well, doesn't matter. But like, let's first review light fields for a moment, because the first papers that fixed this were actually light field-based methods. So just for the record, what is a light field again? A light field is, the point of light field networks or of light field representations was to say, okay, instead of having a 3D representation where we do rendering by sampling lots of points along the array and then doing volume rendering or something like that, we're going to build a representation where the 3D representation itself is actually a function that you just directly query with the ray, and then the representation directly gives you the color for that ray. Do you guys remember that? We discussed these scene representation transformers, we discussed light field networks, and we discussed that these kind of representations were only kind of feasible if you generalized across scenes. Like if you do overfitting, it's not constrained enough. If you do generalization across scenes, you can do stuff like this. So here on the left-hand side is the output of light field networks for these little toy objects, which is rendered by just querying the network with like a single ray and then getting the color immediately. And on the right-hand side, we have PixelNerf, which is a volume rendered representation, which is much slower. Okay? So just as a reminder, any questions on this? Great. So the first paper that tried to tackle this problem of uncertainty used actually a paradigm like this. And it looked like that. Oh yeah, sorry. First, we have to also review denoising diffusion models again, because I'm basically assuming you know how diffusion models work, but just as a reminder, right, on a very high level, you don't have to understand the technical details, but on a very high level, the way diffusion models are trained for images works like that. You take an image, you add noise to it, and then you train a model to denoise it. And then if you want to generate a new image, you start with perfect noise, and you just iteratively apply your denoising model to basically get a new generation, right? Okay, so normally diffusion models are trained on images, and we have lots of images, so there's no problem. As we discussed in the last lecture, there have also been like some attempts of building unconditional generative models, like models that learn to generate 3D scenes with diffusion models. But today we're talking about conditional generative models, and the first paper that kind of took a stab at this was called Normal View Synthesis with Diffusion Models. Great title. So this is actually from friends of ours. Andrea is a long-term collaborator of mine. And they had a very simple idea, which is summarized in this neat little plot here. So this is the training paradigm for this paper. And the way the model is trained, imagine you have a data set like the one that we have discussed so many times before. You have your data set of toy cars. For each car, you have lots of image observations and the camera poses, right? Now you can do the following. You can train a model that takes one image. This is the context image as input. It takes a and then it takes a noisy version of a target image as input. So what we want to do is we want to train our model to generate novel views and to resolve the uncertainty in the novel views. In other words, we want to train a conditional generative model. We want to train a model conditional on a single image, sample from the distribution of images that you could see from this target pose. So what we're going to do is we're going to take a context image from our training set. We're going to get another view of the same object, which we call the target image. We get their relative camera pose, and then we train the model like this. Context, camera pose, stuff both of that into a neural network, and then take the target image, add noise, and then all we do is we ask this model here to denoise the target image. Does that make sense? Questions? Okay, so what do you expect does this... So let's think a little bit about the different... let's think a little bit about what the noise level does, right? So at test time, what do you do at test time? At test time, what you expect this model allows you to do is that you give it just one context image, then you give it some camera pose, an arbitrary camera pose, and then you give it perfect noise. Because, of course, at test time, you don't have the ground truth target image. You don't know. So at test time, you would give it perfect noise, and then you use this as a normal diffusion model. So you ask it, conditioned on this context image and conditioned on the camera pose, which is the camera pose of this image relative to this image, please tell me what this image could look like. Sample from the distribution of plausible images conditioned on my context view. Make sense? Great. So there is not much more. There's not much more to it, except for, of course, you can ask what is like the neural network architecture that you would use to do that. I'm just throwing it up to tell you that there's nothing particularly interesting there. Like the way this neural network architecture looks like, it's a U-net. Who would have thought? And what you do is you have basically a Siamese U-net. So you basically have the clean image, the context image, and the image that you want to denoise. You encode both of them with a U-net, and now the only thing is you want them to talk to each other. You want them to be able to exchange information between the noisy view and the clean view. And so what they did in this paper, which is very common, you see it a lot across these kinds of papers, is that at each level of the U-net, you just have a tension between the features of the clean image and the noisy image. And that's how they basically exchange information. Does that make sense? So there's nothing here to understand necessarily. I'm just telling you you're building this big black box, which basically takes a clean image and a noisy image as input, and then you're basically saying denoise this noisy image conditioned on the clean image, and this is one way of implementing something like that. Yes?
Could you go back? So if let's say my neural network only takes one view of the vehicle and R and T, it's not noise.
Yeah.
And process through the neural network, I shouldn't be able to reconstruct the second view, right? Because I don't know the back of the car.
Well, what do you expect to happen in that case? What do you think, if you try to train it like that, what do you think would happen?
I don't know, but I don't think we can generalize because physically you don't know the back of the car.
Mm-hmm.
I'm confused why adding a little bit random noise would help.
Great question. So there's a few things going on here. So so the question, if I may rephrase, is like why? I think basically what you're asking is like why would this work? So like let's say we don't add this noise and we just added this image and this camera pose. Why would this give you anything reasonable? And the answer is it won't really give you much reasonable things. It will, if you train it just like that, it will, when you change the camera view, you will get like lots of artifacts and stuff, but you will get a reconstruction. In fact, we looked at this before, like a long time ago. We built like a much worse version of this, where we basically had this autoencoder, remember? We just had an autoencoder and we concatenated the target pose in the latent space, and then we decoded it into an image. I could try to find it, but like we had this very naive baseline that we had built. Let me recall that naive baseline. So we discussed this naive baseline where we had like a context image then we built like just an autoencoder, so where we had like an encoder, we had a single latent code, and then here we concatenated the pose to it, and then we decoded it into the target view. And when we looked at that, when we looked at the video that you could render from that, what I think I said back then is like, okay, it didn't really work, but it was impressive that it does anything. And what you saw, it basically is that like, it kind of got it a little bit, but the 3D geometry wasn't quite right. So it turns out that, I mean, I haven't tried this, to be fair. It turns out that the reason why it didn't work had many aspects. One reason was because the architecture that we built was a little bit stupid. It was this architecture of like just having a single latent code, like this global conditioning style. So this architecture here is a little better because it's a UMet. So even if you just gave it this context view as input, then this is still like 6 years later, we now have attention, which is like a different way, like is a different neural network architecture. This would probably give you something reasonable for these simple objects. But it will still be blurry. So the thing that you just said about like we don't know what the back of the car looks like, it's true, the model can't know what the back of the car looks like. But if I show you the front of the car, it's not like you have no idea what the back looks like, right? If I show you this side of the car and I ask you what the other side of the car looks like, you know it's blue, you probably know it has black tires, you know the approximate geometry. So even you could sketch me a version of the other side of the car, right? The thing is you would have uncertainty. You would be like, I don't know exactly, does this part go there or does this part go there? And so this model, you would expect to basically blur over all of these possibilities. So in other words, if you train this model without the noise and you just give it this and this, it'll basically give you blurry reconstructions. And when you render them, they won't be very multi-view consistent. But it'll still do something.
So basically the noise is choosing one sample of the distribution.
Correct. So the noise is basically what the noise allows you to do. Well, it's a good question. So there's actually probably a few things that are going on. So the question was, what does the noise do in this context? So one thing that the noise indeed allows you to do is it allows you to sample from the distribution. So instead of having to collapse the mean, collapse all of the possible reconstructions, it'll allow you to pick one of them. And every noise pattern that you give it leads to a different sample. So it allows you to sample from the distribution. There's another thing, though, that's going on, which is not as well understood for diffusion models, which is that instead of, like, think about the model where you just give it this and that, and then you produce an image. There you just, there's no iterative method there, right? It's just a single feed-forward pass, and it has to give you the correct image. What the diffusion model allows you to do is it actually allows you to iteratively refine your estimate. So in practice, right, the way the diffusion model, when you sample from this thing, instead of a single forward pass, what you actually end up doing is you take context this, you take perfect noise, and then you ask it to denoise the image, and then you add noise again, and you do it again. And then you add noise again, and you do it again. And over time, you decay the noise level, right? And so what has been shown is that what diffusion models do is they do stuff like coarse to fine. So the diffusion model will first generate coarse parts of the geometry and of the car, and then over time, it'll add more high-frequency detail. And so the two parts are, yes, one is it allows you to sample from the distribution, and this one is clear. And the other part is it appears, which is not as well understood, that this kind of iterative processing also gives you something. Does that make sense?
Yeah.
Great. Yes?
Also, the black box that you opened up, it doesn't seem like it's doing anything camera matrix. It's just pair between the.
That's correct, yes. Let me. Test. Okay, I don't know. Does this? Yeah, better. Okay, perfect. Yes, it doesn't do anything interesting with the camera pose. It basically just sticks the camera pose in there and is like, let's see what happens. Somewhat similar to like these to light field network. That's the aspect in which it's like a light field network, basically. It's and in fact, when they say RNT, like there's like some subtlety on how they actually encode the RNT. Actually, in practice, what they do is for each pixel in this image, they actually compute the ray direction and then like the actual ray. And then they concatenate the ray to every pixel, and that's actually how they incorporate But it doesn't actually make a big difference. You can do it either way. It's okay, but good questions. Any other questions? So I think what is good at this, what you can see from this discussion is something interesting, which is that the model gets simpler, but the questions you're asking don't become harder to answer, right? Like the model is actually much simpler. It's like something like some black box and you hit it with a stick, but all of the questions that you're asking are kind of interesting. And let's say I show you now that this model works. Then you're like, this is maybe surprising to you, but the questions remain, like, why does it work? What does the model do? And in fact, okay, so this does work. Let me show you how. This is actually a comparison of the model output to a few of the papers that you already know. SRN is scene representation networks. That's my paper from 2019 that I wrote in my PhD. PixelNerf, we discussed both of these in class, right? So this is a baseline comparison. Input image, output of scene representation networks from 2019, output of PixelNerf from 2021. VisionNerf is like, I actually forgot what VisionNerf does, but it's probably like some other deterministic baseline. And then this is the output of the model. And okay, so this comparison isn't quite fair in a way. But you can see basically the reconstruction looks like really good, right? Like these images look really good. So why is this comparison? So it's kind of entangling two things. Like one thing that it's entangling is this is the only probabilistic method. So this is the only method that can actually generate a non-blurry image. So like that is one aspect that is kind of in there. So these images are sharp. Why are they sharp? Because this model can sample from the probability distribution. So in that sense, the comparison isn't quite fair. These are all deterministic methods, so these have to produce a blurry estimate. So the fact that this thing here produces a blurry estimate is not necessarily a function of the limitations of that model. It's just because it's a deterministic model. So yeah. Okay, but as you can see, the reconstruction looks quite good. Okay, so quick question. So what would you expect if you render the same image several times? So let's say I try to render that image at the bottom there. You give it that input view, and then you render the image one more time. What do you expect? Yeah. That's right. So actually, what is a funny thing about this model is that because this model is a conditional generative model, every time you sample, you will get a different sample from the probability distribution. So in fact, every time you sample, this model might, for instance, give the backlight a different color. Or it might give any part that basically isn't seen in this image might be different in the probability distribution. Of course, though, it's kind of the probability distribution that the model has learned is kind of like an empirical probability distribution, right? So, for instance, if in the training set the color of the back window was always identical to the color of the front window, then conditioned on this image on the left, it'll always give you the same back window color, right? So it'll basically pick up on the correlations. And if it so happens, for instance, that in the training set, you could try this yourself. You could train a model like this. It's not very expensive. In fact, it's cheaper than the models you've trained so far. So if anyone wants to do this for their course project, go ahead. It's probably fun. So in fact, that would be a cool experiment. You could take these cars and now you could make it such that in the training set, this car appears, but the back window color is always different. But the front window color is always the same. And then what you expect is that every time you sample, conditioned on this input image, you'll get a different back window color if the model does a good job. Versus if you make sure that the back window color is always the same as the front window color, it'll always give you the same color. Does that make sense? Okay. That is also kind of bad though, because what happens? When you render this view and when you render that view, these are two different samples from the same model, which means that they could be different. So it could be that in this view, you get this window might be green, and in that view, the window might be red. And there's no way for you to change that, really. Although there's they actually provide a trick in the paper to deal with that, but you have to go and look into the paper. There's not a very principled way of doing this. Okay, so I have the comparison. Let me show you the video. So this is the video. These are reconstructions from the paper. And you can actually see. So let's take a look at this airplane here. If you look carefully, you can see this airplane flicker all the time. And the reason why it flickers is exactly because every image that you see here is actually a sample from the probability distribution, and all of the samples are more or less are not strictly independent because they have a trick in the paper to deal with it, but they are not as consistent as if you had a proper 3D model. right? Like compared to pixel nerf, what does pixel nerf do? Pixel nerf takes the input image and then it gives you one nerf. And no matter where you move the camera, the nerf will always look the same. It won't flicker at all. It'll just be blurry. Everywhere where you have uncertainty, it'll just blur. And this model basically allows you to, instead of getting blur, it'll sample from the probability distribution, but for every camera view, it'll have to sample a new image. Does that make sense? Yeah.
The implication of these are samples from like a Bayesian posterior, or is it more
Yeah, no, that is the implication. It is kind of like you have a prior distribution, although you can't access the prior distribution because the model does not allow you to sample from the prior distribution where you don't give it an image. The model is trained in a way where you always give it the image. You could train it in that way. You could train the model that sometimes you give it an image and sometimes you don't. And then you could say, oh, I can sample from the prior versus the posterior. But I would be surprised if they would actually be like, yeah. Okay, good. Any questions? This is actually all we're going to discuss about. Yeah.
So for the training, how does the image do the similarity between the ground truth image and the
Yeah, just L2. You can use any similarity metric. Good question. Yeah.
because you're not generating one output, you're generating like 5 or 10 outputs maybe. Do you like average the L2 loss over all of them, or how do you
So in this case, I would have to defer you to how diffusion models are trained, which we didn't discuss in class because I kind of assumed that you would. Yeah.
not like for training, but like for like when you're comparing like
Good question. Oh, sorry, I misunderstood your question. Great question. So the question is, when you're computing these, this is a great question. Fantastic. Thanks for asking the question. So I kind of glanced over. This is the table that they have in the paper where they basically report the metrics. So scene representation networks cars, scene representation networks chairs is actually the two. It's funny. These are the data sets that I had introduced in this paper. They're honestly not very well done because I was a PhD student at the time and didn't know what I was doing. And they're kind of a pain. But they report on that data set. Great. And then they're reporting these metrics. So FID, does everyone know what FID is? It's called Fréchet inception distance. It's a distributional metric. What it basically does is it doesn't actually compare two images. It basically just says the images generated from this model, do they look realistic? So this is the normal metric for GANs, right? When you train a GAN and you want to report a quantitative metric, what do? There's no ground truth to compare it to, right? Every time you sample from your GAN, you get an image. What's the ground truth image? Ideally, there doesn't exist one. It's just a generated image. So what people usually report is the Fréchet inception distance, which basically is kind of a hand-wavy metric that says, does this image look like a real image or not? Okay, so that metric kind of makes sense. But then they also report these other two metrics, PSNR and SSIM. And now PSNR is a little bit weird, right? Because PSNR means that I give you an input image, then you produce an output image, and now you compute the error. But as the question suggested, actually this model doesn't produce one output image. It produces a distribution over output images. So why does it make sense to report the PSNR? The answer is it doesn't really make sense to report the PSNR. So you can do the thing that you just suggested. You can say, okay, I'm just going to sample 10 times from my model, and then I'm going to average over the error of all of these 10 images, and that makes sense. In this model, it kind of makes sense because because conditioned on the input, there isn't that much uncertainty. It's still, all of them kind of look reasonable. All the samples look kind of reasonable. But as we go into like some other models later, if you look at some real-world scenes where there's like lots of uncertainty. So for instance, imagine I give you this image as input, and then I turn the camera by 90 degrees, and I want to generate this camera view. Like conditioned on this input view, there's like a lot of possible 3D scenes that I can generate for this view. And if you train the model on like more realistic data than that, then this PSNR metric kind of doesn't make any sense because you can't reconstruct the scene. So the comparing it, benchmarking it on reconstruction doesn't make any sense. Great question. Question? Yeah.
So with this model, is this trained once and then it like works on all those objects like it's general? Or is it like the nerve where it's just
Yeah, no, not a dumb question at all. Yeah, so this is a model that is trained once, and then at test time it generates images just with a signal forward pass.
like, I guess I mean like objects, like where like was the airplane one for that airplane?
Yeah, they just train one big general model, and then at test time, you basically take that model and you can sample it. You don't have to do any fine tuning. It's like trained on just a big data set of objects. No, so the thing that they compare to is PixelNerf. So PixelNerf is also like that. PixelNerf, you also give it you train it, and then at test time, you give it a single image, and then it reconstructs the 3D scene from a single image. So it also doesn't do any fine tuning. Scene representation networks is the autodecoder thing. So scene representation networks is this autodecoder framework that we discussed. So that is also a model where at test time, you give it a single image, and then you optimize this latent code, and then it reconstructs the object. So all of these are generalizable. We call them generalizable scene representations. Other questions? Okay, great, because then we can move on. So now you might ask, so here's a funny little insight. We have models like this one, which these images are all generated by Stable Diffusion. Long story short, Stable Diffusion works really well. And how do you train Stable Diffusion? You train Stable Diffusion by scraping text image pairs from the internet, right? And then you train this diffusion model where you give it a text query, and then you ask it to denoise an image based on the text query. And then at test time, you can generate images like that. Okay, so here's a paper called 0123. And 0123 actually works almost exactly the same as the paper that we just discussed. So it almost works exactly like this paper here, has almost the same input-output behavior. Imagine it works exactly like that. Let me show you the overview figure. So this is the overview figure of 0123. So it's basically the same thing. You have a model, they call it a diffusion model, but basically you give it a context image, you give it a camera pose, and then you give it noise, and the model denoises this image to generate a novel camera view of this object. So same input-output behavior, right? Make sense? Good. What's the difference of 0123? The core insight that they had is, instead of starting from scratch and training our model on like tiny little cute objects, what we're actually going to do is we're going to take Stable Diffusion, which is a model that is pre-trained on like millions of internet images. And Stable Diffusion already has this text thing, right, where you can give it a text query and then it generates an image. And then they just modified Stable Diffusion a tiny bit, such that they basically took the camera pose and they gave it the camera pose instead of the text query. So instead of giving it a text query, they just give it the camera pose. And then they modify it a tiny bit such that they can give it an additional image as input. So basically what they do is they take Stable Diffusion, they basically add one layer in the front where now instead of just giving it noise, they can also concatenate an additional image. And then they give it the RT as just the text. And then what they do is they start with a pre-trained Stable Diffusion model, and they just fine-tune it on a 3D dataset. In fact, they train it on the Objaverse dataset. Objaverse is also a dataset of synthetic objects, kind of like the toy cars that we've looked at. Instead it has 800,000 objects, so it has a lot of objects, and they are much more diverse. But other than that, that's basically it. So this paper came out half a year ago. Okay, so what would you expect this to do? Yeah, okay, so then but first of all, does this make sense? Any questions on this? There's like, no, that's really it. You train it on a larger data set, you start with a pre-trained model. Make sense? So it's kind of a transfer learning thing. So what this model allows you to do is, instead of just generating these toy objects, now you can actually, because it was trained on such a massive amount of data, now you can actually give it photos of real-world objects, and they in fact have a demo on their website. You can actually go on Hugging Face, and you can take a picture of an object right now and upload it, and it works like some percentage of the time. And then it basically allows you to do these 3D reconstructions here, in just the same way as we just discussed it. And so now you're kind of maybe picking up on the trend that we have seen in this research area recently, which is that people were very surprised by this. Why were people surprised by this? The only difference between this model and the other model is basically fine-tuning one of these like really big models and training it on more data. And just by doing those two things and nothing else, like there's zero architectural innovation here, like zero smarts, like no differentiable rendering, nothing. It's like light fields. It's like just nothing. It's just hit it with a stick. Just by scaling it up, you now get a capability that allows you to actually kind of sometimes do it for real-world objects. So like for objects it has definitely never seen before, like for like a bottle, or we could take a picture of my bottle there right now, and it would probably, like I give it like a 60-40 chance that it actually works and the bottle looks reasonable. Quite impressive. So now you might notice that these reconstructions here, they don't flicker as much. Instead, like these reconstructions look very multi-view consistent. So like, and that's because they had another idea, which we actually already discussed last time. So last time at the very end of the lecture, we discussed the score distillation thing. Do you remember that? So the idea of the score distillation model was we can take a pre-trained 2D diffusion model, a model that is trained to only generate images, and then via the smart trick of using that model to basically give you gradients for a 3D reconstruction, you could reconstruct a 3D model with it. Do you remember that? So this is exactly the idea that they also had. So instead of using their 2D diffusion model to render all of these views, what they instead do is they do like a post-processing step. So what they do is they say, okay, so like we have some input image, like let's say, for instance, let's say this was our input image. We take our input image, we give it to our model, and now we query it for, like we randomly pick 50 camera perspectives. And then we say, using all of these camera perspectives, optimize a NeRF such that we can generate all of these images that my model generated. So it's like they basically do score distillation on top of this diffusion model. We're not going to go into detail about score distillation right now because we don't have enough time, and I also I don't have the material to do a good job at explaining that. Who is taking the deep learning class from Philip? Is Philip discussing score distillation in his lecture? But also not in detail. Yeah. It's unfortunately, so if you want to know how this works, you just have to go and read the paper. But like basically the key idea here is that you now have this 2D diffusion model, which basically what it allows you to do is it allows you to generate all of these novel views, right? So you give it a context image, and then it allows you to generate all of these novel views. But these novel views are not 3D consistent, because every time you render, you sample from the distribution of all possible views conditioned on the input view. So in order to get a 3D reconstruction from this, you can do the score distillation trick, where you now basically say, given this context view, optimize a 3D representation such that I can render out all of these views and they all look reasonable according to my 2D diffusion model. Okay. So basically what you do is you have a post-processing step that allows you to distill this 2D model into like a 3D model. Okay, and this is, just for the record, right, this is what we discussed last time. So we discussed this in the context of DreamFusion. So DreamFusion did exactly that thing where they had this 3D NeRF, but whatever. Okay. Last time, we also discussed this problem, though, that what that sometimes gives you is it gives you this thing where when you generate... No, we didn't discuss this last time. Okay, whatever, skip it. Too complicated. Okay, good. We're just going through a few papers, and I'm building up to the paper that I think is the coolest, which is our own. But we're now progressing. So some people, some smart people, like my former group at Stanford, and a few folks at NVIDIA had the following idea. Instead of doing this the complete light field way, where you don't have any differentiable rendering and no 3D structure at all, can we kind of build something that still uses all these insights that we have from PixelNeRF and from all of these differentiable rendering methods, right? And they came up with this method called GenVS, Generative Null View Synthesis with 3D Array Diffusion Models. And actually, I used this figure before in my paper. Let me briefly tell you how it works. Fundamentally, the way this works is that you take an input view. So this is your context view of the object. And now you use this input view to parameterize the PixelNeRF. So you just do generalizable 3D reconstruction from the single image, right? And then what you can do is you can render any target view from that PixelNeRF in this deterministic way. So it'll, if you just trained the PixelNeRF like that, it would give you this blurry reconstruction, right? You could render any target view. And now all they do is they say, okay, let's render out the target view and then use a 2D diffusion model to clean up the blur. They basically say, okay, we just render the target view. The target view is going to be blurry because the model can only generate like a deterministic reconstruction. And now we use a 2D diffusion model that we give this blurry image and we give it the noisy target view, and then we denoise it, and that allows us to get a clean target view. So basically, just a summary, basically you first render out a deterministic image, which is going to be blurry, and then you use a 2D diffusion model to clean it up. Make sense? Okay, good. No questions. Okay. So the things that I want you to hold onto here is that, first of all, this does give you a little bit more like 3D structure apparently. Like you're using all of these things we discussed in the lecture so far, like differentiable rendering and so on, and this like differentiable but fundamentally the thing that is generating novel views is still an image model. It's still an image that takes a blurry version of the image and takes it to a clean version of the image. So this doesn't actually solve the problem of the flicker that you saw earlier. Like when you render novel views, you still have the same property that for all of the parts of the object that you haven't seen before, every time you will sample, it will give you a different sample, right? Does that make sense? Okay, there's also another paper, just for the record, it's called Sparse Fusion, which basically does the same thing, but it's concurrent work from Carnegie Mellon University. Okay, so long story short, these are all 2D generative models. So they're basically all models that have no 3D structure whatsoever, or like limited degrees of 3D structure. All of these models, basically, they allow you to sample images. So they basically say, I'm going to train a big model, a big diffusion model. Given this context image, I want to sample distributions of null views. But they don't directly give you a 3D reconstruction. They don't actually give you immediately a 3D reconstruction. Okay, good. So now we're going to fix that. And this one, so the previous ones we went through really quickly because, but this one we're going to talk about in detail. Good. Okay, so here's the problem. So here's a model that we built some months ago. So given this input view, this is actually a 3D reconstruction. So what you're seeing here are renderings from a NeRF. So, and there is in fact a way of building a model that takes an input view, like a single input image, and then allows you to reconstruct a distribution over all possible 3D scenes, such that every time you sample, you don't get an image, but every time you sample, you actually get a 3D reconstruction of the scene. In that 3D reconstruction, you can then render from arbitrary novel views, and the novel views are always multi-view consistent, so there's no flickering, just by design, because you sampled a 3D reconstruction of the thing. So this is exactly what you can tell here. So you can see that, of course, it's not photorealistic, so like the reconstruction isn't perfect, and there's like some artifacts, but fundamentally, like each of these views are perfectly 3D consistent. There's no flickering in here. And in fact, to convince you of this, here's the depth map that this model gives you. So in other words, condition on this input image, this model allows you to sample from the distribution of all possible 3D scenes that are consistent with that input image. Does that input, yeah? Yeah, good question. So this is an artifact that we see a lot with NeRFs as well. Basically, if you look at this ground here, no matter how many camera views you sample of this ground, the model can always decide, for instance, to replace every black little speckle with a hole, and then just make the background really dark. So that's what this model is doing. The model is basically saying, okay, I don't know which, I think it's like the bright speckles. Every bright speckle, we're just going to replace it with a hole, and then we just make like a background that has that color. And if you want to get rid of it, it would be very easy, but you would have to add like a regularizer that basically says, make the depth map smooth. And there's in fact, another way of putting this is that this is in fact a valid 3D reconstruction. So even if you had 1,000 images of the scene and you reconstructed it with a NeRF, you can still get artifacts like this because it's basically a valid 3D reconstruction. If you have a, I think the only way you get rid of these artifacts is like if the ground is really flat and it just has like different colors, then this artifact will not go away. Just because it's a valid explanation. Like replacing every black thing with like a hole is a perfectly valid 3D reconstruction. You will get perfect renderings from every possible angle. The only reason why you wouldn't get this is if, for instance, the ground had actual 3D structure. So in fact, in this case, if the resolution was much higher of the image, and you could actually see like the geometry of the ground, then you would probably get rid of this because the model wouldn't be able to because then the model actually has to get the 3D geometry of the ground right. But by the way, this is something that many 3D reconstructions have this property that the 3D reconstruction has these artifacts. Like when you look at the depth or if you look at the geometry in many of the NURBS, there's like random holes in the geometry. But this is a very well-known problem. So for instance, imagine that this wall was actually green. It was perfectly green. It didn't have any texture. No matter how many images I capture of this wall, my reconstruction model can always just make this whole panel like a big hole and then paint, or like imagine it like a cave. You can always replace this thing with like a cave, which is like a big hole in the wall, and then just paint the inside of the cave in exactly the same color as this thing. And it's a perfectly valid reconstruction. You can, no matter how many images you capture, like it's undecidable. Which one of the two is it? The only thing that allows you to disambiguate these two things is either if there's texture on the wall, or if there's like things like lighting. Like if you move your head, you see that the lighting changes, and then you could recognize that it's an actual wall. But this is like an ancient problem in multi-view geometry. It's just undecidable if it's just a hole or if it's like an actual panel. Okay, good. So let's talk about how this model works. So now we're going to go into some detail. Actually, no, first I'm going to show you more results. So here's another result from the real estate in K dataset. So here's a single input image, and then these are samples from the generative model. So each of these scenes is a sample from the diffusion model. So you run this diffusion model, and after the denoising is done, you end up with a 3D scene, and then you can render the 3D scene from arbitrary novel views. So in fact, each of these images that you see here the images are not samples from the generative model. Instead, each of these 3D scenes is a sample from the generative model, and then we're just moving the camera. Okay? And as you can see, what that allows you to do is it basically allows you to get flicker-free 3D reconstructions. And what you should also notice is that in all of the parts of the scene that were observed, so these are different samples from the model, in every part of the scene that has been observed in the input image, the reconstructions stay basically the same, and only in the parts of the scene that haven't been observed, when you sample, you get different reconstructions, or different completions rather, it's not reconstructions. Does that make sense? Great. Okay, so how does it work? We faced this problem once before. The problem is that if we denoise images, like if we train an image diffusion model, so like all of the models that we discussed earlier, these are also all image diffusion models, and we discussed how you can train them. It was very straightforward. We pick two images from our data set, we add noise to one of them, and then we ask our diffusion model to denoise that image conditioned on the other one. Easy. So training image diffusion models is easy, but if you want to train a diffusion model that actually generates 3D scenes, then you have a problem, which is that you can't add noise to 3D scenes because you don't have any. Your data set is just images. So you can't do the same trick as with images. You can't, in images, you just take an image, you add noise to it, and you ask your model to denoise it. But we can't do that. We don't have a 3D scene that we can add noise to, and then we can train a model to denoise it. We only have images of 3D scenes. So somehow we have to get smarter. One way that we discussed already is, of course, you could say we first reconstruct. Like we take a lot of time in the pre-processing step, and we first reconstruct all of these different 3D scenes. However, that takes forever, and it's not very scalable. So ideally, we would not want to do that. Ideally, we would want to be able to train a 3D generative model, but we want to train it just from images. How do we do it? I'm going to walk you through it, and I expect that everyone is asking lots of questions because it shouldn't be entirely straightforward. So here's what we do. The input-output behavior is actually the same as the input-output behavior on first side as the input-output behavior of the image diffusion models that we discussed so far. So you go into your training set, and what you do is you get two images and the camera and their relative camera pose out of your training set. So in this case, maybe we pick this one. This is our context view. This is the input to our model. And then we pick one other image, and we get its camera pose, and we get the ground truth image. And now what we're going to do is we're going to do the following. Intuitively, we're going to say, I want you to denoise, like conditioned on the input image, conditioned on this context view at the bottom. I want you to denoise this target view. But the way we're going to denoise it is not just by sticking this into a neural network and then asking it to produce the denoised image. What we're going to do instead is we're going to condition on this and the noisy view, reconstruct a 3D scene. Then we're going to render the 3D scene from the target pose, and that is going to be our denoised image. So we're basically going to build a denoiser where the denoiser itself has a 3D reconstruction step in the middle. So the way that this model learns to denoise images is not by just taking the image and sticking it into a neural network and denoising the image, but instead it takes the noisy image and the clean image, then it reconstructs the 3D scene from both of them, and then it renders it from the target pose to actually generate the clean image. Does that make sense? Okay. And so what's nice about this? There's lots of nice things about this. One thing that is nice about this is that, just for the record, right, just to be clear, at test time, how do you sample a 3D scene? At test time, you would take a picture, you get a picture, and then you pick a random camera pose, like, I don't know, you pick this camera pose, and then you just start with perfect noise at that camera pose. You'll just initialize it with perfect noise, and then you give these two to your, in fact, this is like PixelNerve, but you can pick any 3D reconstruction model you want, but imagine it's PixelNerve. You give these two views to your PixelNerve, that reconstructs a nerve from these two views. One is perfect noise right now, but it doesn't matter. You reconstruct a nerve. And then you render out the target view again, the one that you started with perfect noise. That gives you now a clean image. And now you add noise to it again. You add noise to it again, you do the same thing again. You reconstruct the 3D scene again, you get a reconstruction. And you do that until you arrive at zero noise. So just the same way in which you sample images from an image diffusion model, you sample 3D scenes in this case, because with every denoising step, you get a new estimate of the 3D scene. Does that make sense? Yeah.
So when you start off with the noisy image and the clean image, and then you render a nerve, or not render a nerve, but you like generate a nerve.
Yeah.
And then you're projecting that back into a different camera. That same image back into the model.
So you don't render a different camera pose. You render the same camera pose that you initialized with noise. So you basically take context image, you pick a random camera pose, you initialize it with noise, then you reconstruct the nerve in a single forward pass, like PixelNerve style. Then you render the same view, and that's your denoised version. And then you add noise to that again, and then you do it again.
So for every new pose, you have to do this iterative. For every new camera view, you have to iterate.
Good question. So the question is, do we have to do this for every camera view that we want to render? Can someone answer that question? Yeah.
No, because
Right, exactly. So once you have done this, so like, that's a very good question. So both of you are right. So on first sight, you would say, okay, no, we have actually reconstructed this 3D model, right? So like actually, once you have done this for even just the single context, for just the single view, technically you're done, because now you have your 3D scene and you can render it from any viewpoint. But you're still correct, namely in the following way. How to explain this best? What this model actually does, so one good way of thinking about diffusion models is that diffusion models basically increasingly remove uncertainty from a thing. So, right, when you start with perfect noise, you're basically saying, I'm maximally uncertain about this image. And now with every step of the diffusion model, you're basically taking uncertainty away. Until you're at zero noise you have no uncertainty. At zero noise, you're perfectly certain. You're saying, okay, I've now sampled from my distribution. This is like 100% certain. At the higher noise levels, it's still uncertain at which image you might end up with. You might have seen these cool plots where you basically say, I don't know, like you say, oh, I have my Gaussian distribution, and then on this side here, I have my data distribution, and what, like these might be different images, and basically what a diffusion model does is it starts at like a sample from your distribution, and then it can go here, but maybe here it could also split off and go there. So basically, if you are at perfect noise, then the image that you end up with has lots of uncertainty, but as you are, okay. So what this model here does is it removes uncertainty, but it doesn't remove the uncertainty just from the image. It also it removes the uncertainty from the 3D scene. It's basically saying, okay, conditioned on my context view, just like when we go back to the previous example, right? Conditioned on my context view, I have this reconstruction in the context view. Like when the camera is identical, I have very little uncertainty. I know exactly what the 3D scene. I have a pretty good idea what the 3D scene looks like from this camera angle. So for this part of the scene, I have a pretty good idea. But the moment you start moving the camera, you're uncertain. And so what this process here does is it removes uncertainty from the part of the 3D scene that you are seeing from both of these views. So in other words, it's basically like after you're done with this process, you are like, what parts of the 3D scene are you not uncertain about anymore? The parts of the 3D scene that you're not uncertain about anymore are the parts of the 3D scene that you can see in these two images. But every other part of the 3D scene, every other point in the 3D scene that you don't see from one of these two cameras, you're still uncertain about, because you haven't removed uncertainty from it. Does that make sense? Okay, so good. Now, what do we do to fix that? The way you fix that is by doing autoregressive sampling. So that's a fancy word. What it basically means is you pick this target view. So you denoise this target view condition on this context view. Then you have reconstructed, like then you have removed the uncertainty from those parts of the 3D scene. And now, if you want to maybe, for instance, complete the 360 around the object, you pick another view. And now you treat both of these as inputs. So now you say, I'm denoising a third view conditioned on these two input views. So now you're basically, in every step of the model, you would be treating those two as ground truth inputs, and then you're denoising one target view. Does that make sense? Another thing that you could do is you could say, condition on the context view, I'm denoising all of these views at the same time. That's another thing you could do. Like you could pick 50 views at the same time that like cover the whole 360 around the object, and then you could be denoising all of them at the same time. The reason why we don't do that is because it's crazy expensive. So like training this model here takes, like the model that I just showed you that generates these funny little looking fire hydrants, takes 5 days on 8 A100s, which is expensive. It's not industry level expensive, but it's pretty expensive. It's kind of at the boundary of what we can do at MIT for now. Or at least what we could do at my group. Which honestly is fine. Like, I don't have to be the one that scales and trains this on observers. The interesting part is this part. So, okay. Any more questions about this? Does this, yeah?
So when you test, you start with perfect noise. So can you start with perfect noise when you train?
Great question. So the question is, you're giving my lecture for me. Fantastic. So the question is, do you start with perfect noise? So there's like, clearly there's something, I mean, maybe you already saw it. There's like something else going on here. So I've lied to you a little bit. So there's kind of a problem, right? If you start with perfect noise at this target pose, then the diffusion model can't do much. Because given perfect noise, what is it gonna generate? Like it doesn't, like if you give this part of the model just perfect noise, then this part of the model doesn't know anything about the scene that you have observed. So like, how would it know what scene to generate if you just give it perfect noise? That's a problem. So what you have to do is actually you have to tell this encoder here something about the input image, or something about the scene that it ought to reconstruct. Actually, before we talk about that, like, show of hands, who remembers how Pixelnerf works? Okay, so, because I realized that is kind of a condition on understanding what's going on in this image. So, do people actually understand what's going on in this image? Like when I say we reconstruct the nerf conditioned on these two input views, do people understand what I actually mean by that? How does that literally work? Who doesn't understand how that works? Okay, great. So let me just briefly recap that. So just for the record, I think this is actually an important piece of information. So how does Pixelnerf work, right? We have an input image, context. And now from this input image, we want to reconstruct a 3D scene. Another, okay, and the way that we're going to do that is when we want to decode a 3D coordinate. What is a nerf? A nerf decodes a 3D coordinate into a density and a color, right? And then just for the record, when you render, right, you sample lots of points along the ray, and then you compute this volume rendering integral along the ray. So the only problem that we really have to solve is we need to basically condition on this input image, find a way of decoding these 3D points into colors and densities. So what we do is we take the 3D point, we project it onto the input image, And then at the input image, we get the features at that pixel coordinate. So we have run this image through an image encoder first. So we get the features at this image. And then what we do is we have like a neural network here. Yeah, oh my God. Okay, neural network, obviously. And now what we do is we give this neural network this x coordinate. So we basically give the neural network as input the x, which is the world coordinate, as well as the feature. So here's the feature. We give it the coordinate, and then we get a density and a color from that, and then we can render it. Okay, so that's how Pixelgraph works. So now what we're doing here, maybe that is, so this is exactly the visualization that you're seeing here. To decode, we are decoding a 3D coordinate into a color and a density, and this is volume rendering. So in order to do that, if you imagine for a moment you only had one input view, then it's exactly what we just discussed. You take this 3D coordinate, you project it onto that pixel coordinate, you get the feature at that pixel coordinate that is predicted by this encoder here, get the feature at this pixel coordinate, give it together with the 3D coordinate, give that to the MLP. The MLP gives you the color and the density, and you're done. And now, if you have more than one input view, what you usually do is you get the features from both views and you just take the mean. You get the feature from both of the views and you just get the mean. And so when we denoise this thing, what you can imagine is that this feature initially is the feature that comes from the image that is perfect noise. So initially, one way to think about it is that initially this image, when like the noise level is, when it's perfect noise, this feature has no information content. That feature is just random noise. It's just like, I don't know, no idea what's going on. And the other feature, however, tells you about what it thinks is going on there. And then when you sample, you basically denoise. Okay, and then after the first step, you get like a clean estimate, right? And then you take that clean estimate, you add noise to it again, and then you input it again. And then starting from the second step, basically, this feature here becomes informative. And as you're going from perfect noise to zero noise, you're interpolating between this image has no information to this image has perfect information. Okay, good. Great. So now to address your question, the question is, so when you start with perfect noise here, as we just discussed, when you start with perfect noise here, then this feature doesn't have any information. And so what is this encoder going to do? Like what is this feature going to do? The feature doesn't know anything about the 3D scene. So if you do that in practice, what ends up happening is that this encoder will give you some garbage because it hasn't seen the input view yet. So it doesn't actually know what scene it should reconstruct. It's just going to be, I don't know, it's going to be, okay. So there's an easy fix to this. And the easy fix is simply this. You sample your context view, you take only the pose of the target view, and then you just render a deterministic estimate of the target pose. So you basically first do a forward pass as if it was just pixel nerve. You just do a forward pass, you get a blurry image. It's just going to be blurry. And specifically, as we had seen initially, where is it going to be clear and where is it going to be blurry? In all the parts of the 3D scene that are visible in the context view, it's going to be relatively sharp. And in all of the parts of the 3D scene where it hasn't seen, that weren't observed in the input view, it's going to be blurry. So basically, this image basically tells you where you are uncertain and where you are certain. Then you're concatenating that with noise, and now you give that to the model that we just discussed. So now instead of just giving this encoder the noisy target, you're actually giving it the blurry image and the noisy target. And now, even in the first step, even when you start with perfect noise, this encoder knows what the 3D scene is that it ought to reconstruct. Does that answer your question? Great. Any questions? Okay, so now let's, I had one sneaky slide in between. So earlier we talked about this model here. Right, this model here. So maybe now we can revisit this for a moment, and it makes more sense in the framework that we just discussed. So what this model here is doing is basically this. So what this model here is doing is basically it takes this first deterministic step, so it gets the deterministic estimate of the target image, then it concatenates it with noise, and then it just has a 2D neural network that takes that and gives you the clean image. So that's what I meant when I said this is an image diffusion model. So this model is not actually generating, the 3D scene that could generate that image. Instead, it's just cleaning up the blur, basically. Versus versus this way of actually getting a 3D scene is by taking that thing and doing another step where you basically say, okay, now actually reconstruct the 3D scene that gives me that image. And then you have this guarantee that the final image that you get has actually been generated by the 3D scene. And if you want to generate more images like that, you can just render novel views. Make sense? Great. Fantastic. Now you're up to date on 3D diffusion models, in fact. I wish I could have. I think some of these we discussed already. Okay, more examples. So here is this fire hydrant again. And each of these is a different sample from the conditional generative model. And here you can see a cycle. We stop the video there and we cycle through the different reconstructions. But each of those you can render. So here we're just cycling through the different reconstructions. So if you picked one of them, it wouldn't change at all. It would just be like novel views. Okay, any guess why it only works on fire hydrants and real estate 10K on these indoor scenes? Why don't we train it on more data? Because there isn't any. Because we need camera poses to train the model. And as you know, camera poses are a valuable commodity, which is why all of the models that you can see these days that are trained on real-world scenes are either trained on fire hydrants or on indoor scenes, because those are and there's one more data set which is like outdoor scenes, which is called ACID, where there's drone fly-throughs through outdoor scenes, and that's pretty much it. And then there's a few really small data sets that are there's 20 more scenes that are the typical scenes that we've seen in the Gaussian splatting paper. They reconstruct the scene with the bicycle, or they reconstruct the scene with I don't know, this little garden with okay. There's 20 more of those, but there's basically no large-scale data set with good camera poses. And in fact, finally, Co3D has actually more categories than just the fire hydrants, but the problem is that for all of the other categories, the poses are so bad that you can't actually train any good inverse graphics model on these scenes. So the only fire hydrants is the only class in the Co3D dataset where the camera poses are good enough to train a model that doesn't look complete garbage. So camera poses is a big problem. So think back to 2 lectures ago where we discussed this thing. Really, this is not to be underestimated. It's a huge limitation, but we're getting rid of it. Cool. More hydrants. I mean, I promise you, at some point you'll be sick of seeing fire hydrants. In my line of work, that has actually already happened. So just for a record, so what you see here, this is PixelNerve. So this is a deterministic model, and you can see it's perfectly 3D consistent except for some noise. So where is this noise coming from? The noise is coming from because the rendering is so incredibly expensive. This is volume rendering, right? Because the rendering is so expensive, you have to sample relatively few points along each ray to keep the cost down. And if you sample so few points along the ray, then you don't always get a sample that hits the surface, and that's why along the silhouette you are often getting these how to call it, where the pixels kind of wriggle, and that's because there's not enough samples. If you had 10 times the computational budget, you could just sample 10 times as many points along each ray. It would be 10 times as slow, but hey, and then you could get much higher quality reconstruction. Why is the light on? Doesn't make any sense. No. Off. Okay, maybe not. Anyways, okay, sparse fusion. This is the model. This is an image generative model, as we just discussed. However, what you can see here is actually, this is the score distilled image generative model. So this is, you use this 2D diffusion model to generate these novel views, and then you distill it into a NeRF via score distillation. And as you can see, it doesn't work all that well. It gets the fire hydrant kind of, but yeah. And then these are the reconstructions you get with the model that we just discussed. Cool, more scenes. So here's the real estate 10K data set, lots of kitchens and bedrooms. And there's a few outdoor scenes like this one. But I mean, so this is always the depth map. And I mean, it's pretty cool. So all of these were reconstructed from a single image. And you can do cool stuff here, for instance, right? We're we are basically pulling the camera back and we're leaving the room, and then the model hallucinates the door, right? The model is like, aha, okay, like we're going out of the room, so it's hallucinating the door. Or here, right? So here the model is basically, here the model is hallucinating the parts around the bed, right? Like none of this was observed, and it's basically hallucinating it. If you reconstructed this with a deterministic model, it would just be perfect blur. It would just, the uncertainty in these scenes is so high that there's so many possible 3D reconstructions, it will basically just blur over. It's just going to be any point that isn't seen in any of these scenes, it will just be absolute perfect blur. So for instance, when you if you moved the camera away from this, like this whole part would just be one big blurry mess. So here's the variance. So here we're plotting basically for every pixel in the target view, we are plotting how much this pixel changes as you sample from the model. And as you can see, in all of the parts where in all of the parts of the 3D scene that were observed, the variance is pretty low. There's a few salient exceptions, right? So like this is really interesting. So when you sample for the same camera pose as the input view, then the pixel variance is exactly 0. But you can see here that there's some parts of this image where the variance is high, even though apparently this point was observed in the input view. Does anyone have a guess what is going on there? Why is there uncertainty in that point of the image, in that part of the 3D scene? Where does the uncertainty come from? Maybe you can look at the oven and you can try to figure out what's going on. So here's the oven. So what happens with the oven as we sample? Any guess? Yeah. Exactly. Exactly. Great. Nailed it. So the problem is that conditioned on this input view, even though you have seen these 3D points, the problem is there's scale ambiguity, right? Like you don't actually know, is the oven 10 centimeters further back, but a little bit bigger, or is the oven 10 centimeters further towards you and like a little shorter? You don't know. And there's no way to decide that from the input image. So what the model ends up doing is it ends up sampling from that scale ambiguity as well. Conditioned on the input view, it doesn't know exactly how far things are away. So every time you sample, you get the scale ambiguity. And that's why for the input view, even though there is the scale ambiguity is just along each ray. So like the input image doesn't change. Like in the input image, there's no uncertainty. Like you're just moving, like if the oven is a little bit bigger, you're just moving it back and you're making it bigger, the input view is not going to change. Only the other view is going to change because from the other perspective, you actually see the oven moving. Does that make sense? So this tells you something about monocular depth estimation, which is that monocular depth estimation is not a deterministic problem. So we talked about monocular depth estimation before at the very beginning of this course, and we discussed all of these different models. Note that all of these models were deterministic models. All of these models produced one estimate of the depth conditioned on the input image, where in reality, it's not actually a deterministic problem. Conditioned on the input view, you actually get a distribution over possible depths, and the depth is basically uncertain according to the uncertainty that you have in scale. So for instance, if I took an image of this chair, and I showed you that thing, there's no way on the world, unless you know exactly which model of chair this is, and you go look it up in the catalog of the producer, there's no way for you to decide how big the chair is from the single image. But you have error bars. You're like, okay, it could be like a little smaller and closer, or like a little bit further away and bigger. And that's the uncertainty you would expect to be able to sample from. And in fact, there is a paper from David Fried at the University of Toronto, which is called The Surprising Effectiveness of Diffusion Models for Monocular Depth Estimation and Optical Flow, where they basically, the only thing that they do in the paper is they basically say, okay, here's a monocular depth estimation model. Let's replace it with a diffusion model. And then you observe exactly the same thing. You train it on a supervised data set, so they have just image pairs. They have image plus depth, and they just train a supervised model. But instead of having a deterministic model, they train a diffusion model, and then you observe exactly that. Every time you sample, you basically get a different sample that is still consistent with the input image, but you just sample from the uncertainties. And there's like lots of ways in which you might have uncertainty. Like sometimes you have stuff like maybe something is like, maybe it's a low resolution image, and in the back you're not sure, is that like a hole in the wall that leads to the other room, or is it an image? Then when you sample, you can see actually sometimes it makes it a hole, and sometimes it makes it part of the wall. So this is actually kind of an interesting thing. And it turns out in vision, I guarantee you any problem that you're doing research on actually has, in the real world, every problem has uncertainty. So in the real world, if you're solving an inverse problem, so if you're solving a problem when you're solving for some latent variable, when you're solving for some latent variable from incomplete observations, which is basically all of research, right? You always have uncertainty. It's never the case that conditioned on the input image, you know exactly what the target looks like. Otherwise, you wouldn't have to solve the inverse problem. So usually, it always makes sense to think about building a probabilistic model. And so far, the problem is that these probabilistic models were really hard to build. So I actually, like as I was starting this lecture, I realized I wish I would have put that in here. This is like a really old problem. People have tried to tackle this problem in many ways with VAEs, with GANs, and the very first paper on neural scene representation and rendering, which coined that term, neural scene representation and rendering, is actually a paper from DeepMind from 2018. So it's like 2015, I think. So it's like pretty long ago. This was kind of what got like one of the papers that I was reading when I was getting into this research direction. They used a so-called latent variable model, which is kind of a, we're not going to talk about it, but it was like a really complicated model. It's like a really complicated model with like prior, posterior, KL divergence, this KL divergence here. It's a science paper, so it's a paper published in Science. And I encourage you to read the paper and read it very carefully. On the first slide, it looks like a VAE, but it's not a VAE. It's very, very different from a VAE. And if you go look at that paper, they can only do it on these tiny toy scenes. It doesn't actually work on real-world scenes. And one of the reasons for, so this paper here is something that I've been working on for since I started doing research on this topic. And this is the first time that we were able to solve this problem in the real world, like sampling from the distribution of 3D scenes that are consistent with input images has been a long-standing problem. And the key piece turns out to be diffusion models. So the thing that made this feasible now, where it wasn't feasible before, was because kind of all these other models, they do not give you an objective that you can efficiently optimize. Where diffusion models turn out, they give you a really, really, really neat way of solving this problem. And I'm going to ramble on a little bit more about this because I think it's really worth talking more about. But what is so special about diffusion models is that, like, let's think for a moment about a GAN, right? What does a GAN do? You could think about like building a version of this model that looks like a GAN, and maybe what you would do there is you would take this context view, and then you would generate a random noise vector, and then you would give that to a model that takes that random noise vector and this input view, and then it outputs an image, right? And then you have a discriminator on that image. That's how you could build like a GAN version of this thing, right? That doesn't work. It's going to die. There's no way you can train that. It's like absolutely not working. The key difference between like all of the prior kind of generative models and diffusion models is that diffusion models give you this really neat way of interpolating between sampling from the like what you previously called the prior and the posterior. If you give the model complete noise, then it's kind of like a GAN. Then you're basically saying, okay, I don't know anything about this target image. Just sample from the distribution as if you know nothing. But in the other limit, when you give this model at training time, this image with very little noise, then it's kind of like training PixelNerf. Then you're basically, it's not like training PixelNerf. Then it's basically like the model has to only guess a tiny part, right? The model has to just, okay, there's a little bit of noise in here, and I only have to guess these tiny little parts of noise. And it turns out that what that gives you is it gives you a training objective that is really easy to optimize. Because when you give the model, when you sample at training time low noise levels and you add very little noise to the model, then the model only has to guess very little, which means it gets really nice gradients. It's like it's hard to get it wrong, so to speak, right? The model will always do a reasonable job at it. It's like, okay, I have to remove this tiny bit of noise, no problem. And then, so sometimes the model gets like lots of noise, sometimes the model gets little noise, and in the cases where it gets little noise, it's very easy. In the cases where it gets lots of noise, it's very hard. So this is something that is very unique about diffusion models, that they allow you to interpolate between the case where you have perfect uncertainty and the case where you have no uncertainty. Questions? So this is like really important. If you're doing research on anything like this right now, this is like something to think about. Okay, good. One more word about this model. This paper is called Diffusion with Forward Models. It's not called diffusion for 3D reconstruction. Why is it called diffusion with forward models? It's because you can replace the differentiable render in this with any differentiable forward model. So if you, in fact, in the paper, we show two other forward models. One is optical flow, and the other one is scan inversion. So if you, in your research, have a problem where you have to solve an inverse problem, such that you get an input, and conditioned on the input, you have to reconstruct something that you don't observe directly, but instead you observe it through a lossy forward model. Like, for instance, in this case, we want to learn a generative model for 3D scenes, but we only have images of 3D scenes. Maybe in your case, you want to reconstruct proteins, and you only have tomography observations of the proteins. Or maybe, I don't know, maybe you want to reconstruct black holes, but you only have, over time, you have like where's the native speaker? Thank you. Interferometry, thank you for nailed it. Interferometry observations of that black hole. As long as your forward model is differentiable, you can stick it into the same framework where you basically say, pick two observations of the thing that I want to reconstruct, add noise to one of them, then do the same thing here, just with whatever forward model you have, might be a different forward model. That allows you to reconstruct the thing that generated both of these observations, generate both of these observations, and train it end to end. And that's really cool. There's also a whole proof in the paper. So yeah, this is a cool paper. Okay, and that's actually the end of the lecture. Thank you. Oh yeah, question.
So the bottleneck in like applying this to like other applications, like interferometry, for example.
The key bottleneck usually is that in many other applications, you don't always have several observations of the same thing. So sometimes the thing, I think that's a key bottleneck. Yeah, and then data, of course. Yeah, you need lots of. In this case, you need lots of 3D scenes, and for each 3D scene, you need a few images, and that would have to be the same for you. So you need some application where you have lots of things that you want to reconstruct, and for each of them, you have a few observations. Thank you.